Hello everyone, I hope that you are fine. I welcome you to another lecture of robotics, and today our lecture is about path search algorithm. So let's have a quick overview of our today's topic that we are going to cover. We shall first recall our navigation topic that we have discussed in the previous lectures. We defined what was navigation. Navigation was the ability of the robot to find its location in the environment. The robot should know that where I am now in the map or in the environment, and then the robot should also able to make a model of the environment or the map of the environment. So it should know that where the obstacles are located in the map or in the environment. Then we said that okay, after localization and mapping, we said that okay, now the robot should able to search the path toward the target or the destination. Okay, and for that we used grid methods. In the previous lecture we used grid method for path planning, and if you remember, it was the wavefront algorithm we used to find a path from start location to the target location. And then also briefly at the end of the lecture we also talked about graph, what are the graphs and what are the edges, what are the nodes. And then we also discuss about a little bit about the breadth-first search algorithm that can search a path or a shortest path in a graph. So today we shall see the further some types of graph search algorithms and where they are applied and how they work. Especially we shall talk about the breadth-first search algorithm, and we shall see how we can apply it on the graph and how we can apply it in the grid. Then we shall learn about Dijkstra's algorithm. This is another graph search algorithm, and we shall see the difference between the breadth-first search and the graphs and the Dijkstra's algorithm. After that there is A-star algorithm. This is an informed version of Dijkstra's algorithm, and we shall also learn today how to find the shortest path using A-star algorithm. There is another type of algorithm. It's a method of creating a graph. It's called visibility graph. We shall also briefly we see that how it works, because it's not used much. It's not that common, but we shall see, and in a few minutes we shall discuss it. Then we shall learn about sampling based algorithms, especially the RRT algorithm and the RRT star algorithm. And finally we shall there is one more thing I forgot to here, right? It's probabilistic roadmaps. So you should also have a look on it, how it works. So let's move forward. Shortest path in a grid and graph. So what is a shortest path? If you want to define what is a shortest path, shortest path can be a path that has the smallest length from start to target position. Okay, but it's not always about length. Okay, it's sometimes about some other parameter. For example, energy. If you want a path with minimum fuel consumption from one location to another location, then this path will be a shortest path with respect to your fuel consumption. And same is true for other parameter. For example, time. If you want the shortest path with respect to time, then yes, I think you can apply the same method here. So the goal of path planning is, as we have seen in the previous lectures, this is, let's say this is a start location we have, and this is the obstacle, this is the target location, and this whole is our environment, or the C space, or the configuration space. This is a space where a robot can move around, and the white cells, they represent the free space. The robot can move here. The black cell mean there is an obstacle, so robot is not allowed to go there. So, and it's clear from this picture that this is a discrete map, because we have divided the whole C space into cells, or you can say a grid. So this is also a grid-based map, you can say. So the goal of the path search algorithm is to search a path from start position to your target location here, from this green to red box. So one quality of this path, which is that one task is to search the goal, and the second task of the path planner is to have a path that is shortest. I mean, it should not be like this path coming from here. It should be a shortest path with respect to either length or some other kind of criteria. So these are two goals of our path planners. So yes, and so there are specific algorithms for grid search, like we discussed one in the previous lecture, which like wavefront algorithm. It was specifically designed for grids only. And also there are algorithms for graph search also. Graph search algorithms, they work on graphs. If you remember what is a graph, graph is a collection of nodes and edges. So there were some different types of graphs, like directed graphs or undirected graphs, and then there were weighted graphs, if you recall the previous lecture. So graph search algorithms, as I said, they can be applied on a graph, and they can also be applied on a grid with some, if we convert the grid into a graph. Recall the previous lecture in which we learned about how to represent a grid as a graph. Okay, then we have algorithms, for example, sampling based algorithms. They are different types. They don't use a grid, they don't use how to say, this typical deterministic method. Instead, they use some kind of random sampling of your configuration space, or you can say the C space, to search a path in the environment. We shall learn these kind of algorithms later. So first, let's see the path search in a discrete map. How we can do that. So the first thing we have learned that if we have this kind of discrete map, then we can use simply a wavefront algorithm, and then we can find the shortest path from start to target position. There is another method we learned, that we can convert this grid into a graph, in which we have some nodes, and these nodes are connected by edges. So this connectivity we have learned in the previous lecture. This can be four neighborhood nodes. If there are four neighborhood nodes, then it means they are connected only to vertically and horizontally, but not diagonally. So, for example, this node can have four neighbors: 1, 2, 3, and 4. And the side nodes can have 2 neighbors. So this is how we convert a grid into a graph, in which we have nodes here, and also we have edges. So this is a node here we have. And this is we have edges. So once we convert a grid into graph, then we can apply some kind of graph search algorithm to search a shortest path in this graph. But if you don't want to do that, you can just apply directly wavefront algorithm that is specifically designed for grid, and that will also find the shortest path from start to target position using just without conversion into any graph. Okay. Yes, this we already have discussed, grid as a graph representation. Okay, sometimes let me tell you why the graphs are more important. Sometimes we see that this was a grid map. Okay, this is a grid map, and we learned that how to make that in the previous lecture also, and also in the lab. So this is a kind of discrete map. Discrete means it has some discrete cells, and this is in contrast to this discrete map, we have also a continuous map. So this is, for example, this is an example of a continuous map. So in continuous map, how we can do path planning here? How we can, for example, this is our start location, and this is our this target location here, and our robots want to move from this position to target. So can we do path planning or path search without using discrete map? In this case, we only have a continuous map. So how can we do that? One way is to do that is to make some kind of model the free space using a graph. We can say that, okay, we have here some points here, some nodes you can say, and we can make one point here also, and then we connect these points, and we say that, okay, these are the possible paths in this whole environment, or in a map, or a room map. So this is how we can reach our target. These are the possible, you can say, routes we have. There can be more points also, but let's say they are only. So this is another method to model the environment using a continuous map. Once you have a continuous map, you can make a graph here, and then use a path search algorithm to find a shortest path in this graph. We shall see in the next slide how to do that. Okay, so this is our first simplest algorithm, breadth first search. In the previous lecture, we just introduced it, and today we shall see how it works in detail. So this is our graph here, and so this A is a start node, and F is, let's say, our target node we have here. So, and these are the intermediate nodes B, C, D, E. So these are the intermediate nodes we have. And now you must be wondering, okay, why, from where this graph come from and why we are doing it. Okay, so just to remind you guys why we are doing it, again, just look at this previous slide and remember that the graph comes from either from the grid or either from the direct continuous map. Okay, so the graph models your environment. It represents where the free space is, where the robot is allowed to move. Okay, so this graph, it came from, let's say, some kind of map, a continuous map, or let's say it's a continuous map, and so we model it and make it as a graph. And so you can say A, B, C, D, E. They can be rooms, they can be cities, and these edges, these lines, they show their connectivity. It means that you can go from point A to point D, but you cannot go from point A to point C. So it means that there must be some kind of obstacle between A and C. So the robot cannot go there. And yes, same is true for other also. So now our first goal is to find where our target is located, where our destination is located. Let's say our robot is at point A and it wants to search where is the T, in which point, in which city, or in which room the point T is located. So how can we do that? For this purpose we have a special algorithm. It's called breadth first search. It's a simple one. It's a graph traversal algorithm that can be used to find a path or to search a path in a graph. So the inputs to this algorithm is you need a graph, for example, a collection of nodes and edges, and then you need some start point and also target point. So how it actually works, how it searches the other points. So what it basically does, it visits the nearest nodes first. Okay, this is its primary strategy. If it starts from, for example, A, then it will always visit the nearest nodes to the A, like D and B. So layer-wise graph traversal. Layer-wise means that, for example, this is a graph, and we also see that, let me show you here. You remember we also studied the difference between a graph and a tree. A tree is a special type of graph in which each node has only one parent, but a parent node can have multiple child nodes. This makes sense, or? So this is root node, and then we have it has two children. Let's say this is node A, node B, node C, and then we have D, E, F, G. Okay, so this is a root node, which is A, and then we have its two child nodes, B and C, and B has further two children, D and E, and C has further two children, F and G. So, and you notice that here, because this is a tree, so each children node or each node can only have one parent. If you look at D, it has only one parent, B. If you look at B, it has only single parent, A. And same is true for all of the nodes. So what this breadth first search algorithm do, it let me change the color. So what it searches the graph layer wise, like we discussed in the slide. First it will start from here. After that, it searches the next neighboring or adjacent nodes. So these two nodes are B and C are adjacent nodes. These are adjacent nodes to A. Okay, and once it has traversed these nodes, it has searched these nodes, it has found these two nodes, then it will, the breadth first search algorithm, I write only BFS, like breadth first search. So okay, once it has reached here, then it will search for the neighbors of B and C. So the next level will be this one. Okay, so this is the breadth first search algorithm we have. It will keep repeating till it reaches the end of the tree. So that's why we call it layer wise graph traversal. And one speciality of this kind of algorithm, BFS algorithm, is that it works on unweighted graphs. Recall from the previous lecture what was unweighted graph. Unweighted graph was the graph in which the edges have no weights. There are no values on the edges, so all are same. You can say all have the value 1. So this kind of algorithm, it works only on unweighted graph. That's important. Okay, now we shall see step by step how we can search the graph using breadth first search algorithm or BFS algorithm. So the first step is assign all nodes as not visited. So this is our graph. We say the node A, B, C, D, E, F, all of them are not visited in the algorithm. Okay, when we write algorithm, for example in Python language or in MATLAB or in C++, any language where you write your algorithm, I hope that you remember what is algorithm, and we studied it in the previous lectures. So when you write algorithm, so the first step you will do is to assign all nodes as not visited. So starting from this point A, you say that all other nodes in the graph A, B, C, D, E, F, they all not visited because we haven't visited them, or you can say the algorithm haven't visited them. So let's see what is the second step. Make a queue. So this is also the second step, is you have to make a queue. So what is a queue? Queue is the actually in your programming, in your algorithm or coding, when you develop some C++ or Python coding, so you define some structure, some kind of memory elements and one of them is Q. And the speciality of Q is it's the first in, first out. Okay, if you, for example, if you put something in a queue in a specific manner, so the thing that you put first, it will come out also first. So this is like you put something in the line, you can say. So yeah, so in the next step we have made a queue. You can just imagine a queue as some kind of memory in your computer, in your coding. And the next step is add start node to queue and make it like label it as a discovered. So our start node is A, so we put here A. Okay, so once we call it A is now discovered, and because we have found the A. The next step of the algorithm is add adjacent nodes to queue. So what we have to do now, we have to look the neighboring nodes of A. Okay, what are the neighboring nodes? Look at here in this graph. The neighboring nodes of A are D and B. So these two we have. So we put them in alphabetical order. We say that okay, the neighboring or the adjacent nodes of A are B and C. Okay, once we have done that, then what we do, we assign distance and parent node to discovered adjacent nodes. So now we have to assign the distance of each node from starting node. So because A is itself a starting node, so it should have a distance 0, and its parent is no, it has no parent. I call it nil. So distance is 0. This on the left side we have distance, and on the right side the parent to this node is no one, because A is itself a starting node. Okay, now look at the B. B has a distance from A is 1. 1 is distance, and its parent is A. Okay, so this distance, because it's an unweighted graph, the edges have same kind of weights, so it doesn't matter. So we take it like, let's say it's a 1, and the distance is 1, so it's 1 step away from A. So that's why we have assigned this value. And now same we do for the node D. So the node D is 1 step away from A, so we call it 1, and its parent is A, because it is connected to, we are coming from A to D, so the D parent is A, or you can say the child of A is D. So 1A. So now we have assigned the value and parents of each adjacent node of A, or you can say a neighboring node of A. Now let's see what is the next step. Remove the top visited node from queue. Okay, so now what we do is that we remove it this node, the first node that we enter in the queue, then we shall remove this node first. Okay, that's why it's called queue, because you enter and you delete also, and also when it moves to the next nodes, it will also follow this kind of queue fashion. Okay, so we have removed it. Now A is no more in the queue, and make the next adjacent nodes as visited node and discover its neighbors. Okay, so next what we do here, we move from A now to B. Okay, we call it, okay, B is now visited. Now we are at B. So previously we were at A, but now we are at B. And from here we shall do the same process. We shall repeat the same process. What we shall do here, we shall see, okay, what are the adjacent nodes or the neighboring nodes of node B, which is C and A. We have two neighboring nodes. Unfortunately, the A is already visited, and so we will not go there. So what we do, we discover now the C. Okay, so what we do, we try to now calculate the value of the distance and the parent of C. So what is the distance of C from node A? It's 1 plus 1, 2, and its parent is B. Let me explain that. So you have to see the distance of node C from node A, although your starting node. Okay, so from A to B the distance was 1 and it's written on the B, and from B to C again it was 1. So 1 plus 1, the total distance is 2. So it means the C is 2 steps away from starting position, and its parent is B because it is directly connected to B. So we are coming from B to C. Okay. Now we have explored C. There is a mistake here. I have made a mistake here, and because this is not C, because A was connected to B and D, not the C. So here it was not C. So that was my mistake. I corrected. So from A we put B and C in our queue. B and D in the queue. So here I should write here D here. So A was connected to B and D, and after that we have visited B. So once we have visited B, we shall remove it from the queue, and then we go to next, we move to D, this node D here, and we shall explore what are the neighbors of node D, or what are the adjacent nodes to this node. So you can see D has two neighbors, one is A and second is E. So we have discovered one new neighbor, which is E. So what we do, we put this in the queue here. So, and we shall not put A because A was already visited. We have already calculated its distance and its other stuff. We have visited it. So we only now search for undiscovered nodes that are not previously discovered or visited. So from D to E, now we repeat this step. We shall calculate the distance and the parent of node E. So you can say the node E is one step away from node D, and node D is one step away from node A. So it will be 1 plus 1, 2, and its parent will be node D. Okay, so here there is a small confusion, and sometimes it's difficult to grasp. From here you can see that this node E has actually two parents. It has one parent C and the second parent is D. So which one is the real parent? So in breadth-first search, the parent is the one from where we are coming from. Okay, right now we are at node D here. Okay, and from we are looking the children of D. So D is the E is the children of D, or you can say E is the parent of node D. Or I think it's other way around. It means the E is the children of D and D is a parent of E. So that's why we will not consider C as a parent, although it is a parent, but in this algorithm we shall not consider it as a parent because only one can be parent. Okay, now we are at now we have visited node D. We have explored all its neighbors or its adjacent nodes. Now what we do, we say, okay, this is visited already. We have visited it. Let's make it this sign, and then we remove node D from the queue. And now we have only node E in the queue. Now we shall jump to node E. Okay, and we shall explore its neighbors. What are its neighbors now? When we are at node E, we looked at it has three neighbors, C, D, and F. C and D are already visited, or they are already discovered, you can say. Okay, but F is not till yet discovered. So what we do, we have discovered F and we put it in the queue here. So we have found a new node here. Okay, so now we repeat the same step. We shall calculate its distance, which is the distance of node E plus one step further, which is 3, and the parent is E. So here you have seen that we have now reached our target node, and so now what the algorithm will do now is that, okay, E is already visited. We shall also remove the E from the queue, and then when we move to the node F, then we shall look that it has no neighboring nodes, or it has no adjacent nodes. So we shall end our algorithm here. Actually, the algorithm, you can say we should stop algorithm here, not end. There is one more step which you may or may not include in breadth-first search. Till here, so what we do here, since F has no further neighboring nodes, so we shall remove it also from our queue. Now there are no more nodes in the queue. It means that we stop here the algorithm. And now what we do here, till now what we have discovered all nodes in the graph. You see that we know how many nodes are there. We also know, or the algorithm knows, what are the distance of these nodes from the graph and where is our target node located. We have searched, we have found our target node, which is F. So this is the first step completed, which was search the target or search the goal. So this algorithm has successfully searched through this graph and reached this goal here, which is F. Now the thing is, we have to make a path. How the robot, because there are multiple paths from start position to the target node F. One path is like A, going from A to B, then B to C, C to E, and then F. And the second path is like A to D, D to E, E to F. So which one is the shortest path? Which one is the best path you can have? So what you need to do here, you need to follow the parent nodes of each node. For example, starting from node F, start from node F and look at that what are its parents. So here you can see that on the right top corner of node F, it's written that its parent is E. So we just from F we move to E. And then we look at what was a parent node of node E, and it's node D here, it's written here. So we move to node D. And then same, we repeat this procedure from the parent of D is node A. So that's how this is the shortest path. Have you seen that? So actually it will be in reverse. So let me change the color. Make it red, okay. So when the robot moves from A, it will go directly to node D and then node E, and then it will reach F, the final target node. This is how it will happen. So the robot will start from node A, and then it will go to node D, and from here it will move to node E, and then here it will move to node F. And you see that the total distance of this path is 1 plus 1 plus 1, 3. It's three steps. But if you see the other alternate distance, the other path could be like A to B to C to E to F. It will be 4. The total distance of this alternate path will be 4. So you see that how this breadth first search algorithm, it has first successfully searched where the target is located, where your goal is located, and then it also find a path which is the shortest one in this graph. So this is the advantage of using breadth first search algorithm. It is actually the simplest algorithm in the path planning or the path search algorithm. Specifically for graph search algorithms, you can say this is the simplest one, and it only works on the unweighted graph. Okay, so I hope that this is clear. Now let's see that how it works on the grid. So let's say we have a grid. This is our grid map, discrete grid map, and we have here, this is our start position here, and this is the target position. In this one we have obstacles, and the white space is a free space. So now how we shall apply here the breadth first search algorithm. So again, let's say in this example we can have two types of connectivity. We can have we can say the nodes, either each node is connected to 4 nodes, which is horizontal or vertical. So each node is connected to 4 other cells, or each cell is connected to 4 neighboring or 4 adjacent cells. This is the 4 connectivity. We have also studied 8 connectivity, in which there was also diagonal connections also, but it just makes your graph more complex. And if you consider the 4 connectivity, then it will be simple. And also one thing is that if you use 8 connectivity, then your path will be shortest, because let's say if you want to move from this node to this node, so if there is only diagonal or vertical connections, okay, if there are only these kind of connections, then going from node 1 n1 to node, let's say 4, it will require like going to here, this distance plus this distance. But if you have, this is for 4 connectivity, okay, there are only connections horizontal or vertical. But if there is an 8 connectivity, then you have also this diagonal connection. So this will be shortest path from n1 to n4. Instead of going here and then here, this will be your shortest path. So it means that if you have 8 connectivity, your path will be shortest as compared to if you have 4 connectivity. But it will be more complex because you have more number of now neighbors to deal with. Your queue will be more larger. So yeah. So just for example, we take only 4 connectivity. It means this starting node, it is connected with the only 2 nodes here. So what we do here, we when we apply breadth first search algorithm here, so it will look at the neighboring nodes. So this node here and this node here. Only if we take 4 connectivity, we ignore this kind of diagonal connectivity. So the distance from we calculate the distance from this node, and then we say that okay, the distance was 1, let's say, and here also the distance was 1, and the parent of this node is the first we have to change the color of our pen and make it a different color. Okay, let's say blue we have. So first thing, we have to give the numbers here also. This is number A, node number A. This is node number B, and we have C, D, E, G, H, I, J, K, L, N, O, P, Q, R, S, T, U, and V. Okay. So here how we shall traverse here in this grid one. So we know that the distance from, so here the easy thing is we know the coordinates of each node here. We know that, for example, this is node number 1 here, node number 2, 3, 4. Okay, it's not node number, but it's actually the coordinates of these nodes. So okay, starting from node S, or sorry, node A, which is the start point, we shall, if we apply breadth first search algorithm, then when we go to node number B, it will have 1, the distance will be 1, and the parent of this node will be, let's say, A. And same is true for the node number F. The parent of it will be A. Okay, in the second, after that we once we explore this the neighborhood, then we go to our next node, which is the B, and we explore its neighbor. So from B, if you look, we have two neighbors. One is G and the second one is the C. So again we have here, if we see the distance of C from A, then it will be 2, which is the distance from A to B plus B to C, which is 1 plus 1. And the parent of this node C is node B. Okay, and same is true for node G. Node G will have a distance of 2 and its parent will be B. Now according to the algorithm, now we have to, in the queue we have node F, and when we come visit the node F, then we see that it has a neighbor G, it has a neighbor this here, but this is blocked, this is obstacle, this is not a free space, so the algorithm is not allowed to go there. And the third neighbor is the node A, which is already have been visited. So there is no other undiscovered node from, if we look from node F. So we will just let it like this. Okay, we don't do anything. And now the next nodes we have in the queue, we have C and G. So let's visit the node C, and node C will have further two neighbors. Okay, so this neighbor will have cost 3 and its parent will be node C. Similarly, this node D will have a distance of 3 from A and its parent will be C. And now when we visit our node H will have neighborhood of node G, B, C. So not B, because we are only seeing the diagonal and vertical one. So node H will have a neighbor node G, node I, node C, and this here the obstacle node. So but G is already visited and C is already visited, so it is not allowed to visit it again or discover it again. So, and also this side we have obstacle, it is not allowed to discover it. So the only option is it can go here, it can visit here, I. So when we visit here, we say that okay, we have the, so here there is a small mistake here. Let me correct it. So when we visited node C, we explored nodes D and H, and we said that okay, these are the two neighboring nodes that should be discovered, and we discovered it by C, and we assigned the values of each of their distance and their parent. And then after that we have to, the next move is, because we are following the alphabetical order, so we should explore node D, not node H. So first we explore node D and then we come to H. So this is till now this is not correct. So now we are now at node D, and at node D we see that we have two neighbors, node I and node E, and these neighbors has a distance of 4 and its parent is node D, and here we have for I the distance is 3 plus 1, which is 4, and its parent is node D. Okay, and now once we have explored these two nodes, now we go back to node H, and you see that node H has no option to explore because all the neighboring nodes are either already explored, or they are either already visited, or they are blocked by the obstacle. Okay, so we shall remove H from the queue, and now we have two nodes, E and I, in the queue. So from node E, we see that it has only one neighbor that need to be explored. The other two neighbors are already discovered. So it has a distance of 5 and a parent of E. And now we come to the node I, and node I has only one neighbor. The other neighbors it has more neighbors, but one undiscovered neighbor, so which has a distance of 5 from the start point, from the node A, and its parent is I. And now we go to the node number J. It has again one undiscovered neighbor, which has a distance 6, and its parent is J. And similarly, now we return to K. It has one undiscovered neighbor, which has a distance 6 and a parent K, and we repeat this process L and 7. Okay, so now we have two nodes, P and Q. So P has the priority alphabetically. So let's see, P has how many neighbors we have. It has this U unexplored neighbor and O. So here we write 7, and its parent is P, and here we write 7 and its parent is P. And now we go to node number Q, and we see that it has also one unexplored neighbor. Distance is 8, and its parent is Q. Okay, now we have how many nodes we have? O, U, and V. So alphabetically we have here O node gets priority. It should be discovered first. So if we see here, this node has 1 and 2 neighbors, and the distance of this neighbor from start position is 7 plus 1, 8, and its parent is O, and 7 plus 1, 8, and its parent is also O. So now we come back to the other previous nodes that were unexplored, that were U and V. They don't have any other option because all of their neighbors are either they are discovered, or they have already visited, or the other neighbors don't exist. So now we have two nodes now that are in the queue, which are the node number N and T. So from here, alphabetically node N gets priority, and we see that this node has two neighbors, M and S. So node M is 9 steps away from source, and its parent is the N, and here we have to change the color. let's make it black here. From here, this is 9 steps away and its parent is O. Okay, now we have discovered these nodes and we M and S, but we also have a node, this T, in the queue. So now this T is it should be removed from the queue because all the neighbors nodes of this T node, they are already either visited or discovered, so it should be removed. And now we have 2 nodes in the queue which are M and S. So alphabetically, node M gets priority, and let's see, it has only one neighbor that is undiscovered, and this has a total distance of 10 and its parent is M. So once we reach here, we see that this node R and node S, they don't have any further possibility to, they don't have any further undiscovered neighbors, so we shall remove them from the queue, and then finally the queue will be empty. And once the queue is empty, it means we have explored, we have discovered all the nodes in your grid. And now it's time to find the goal. So goal finding is easy because we know that the goal is here, and this algorithm has successfully find our goal, which is this is one of the node, and it has a shortest distance of 9 steps from your starting node. So the minimum distance is 9 we have. If you move from S to from your target node to your start node, it will take 9 steps. So let's draw the path using this parent method. Okay, starting from here, we just follow the neighbors. So S has a parent of O. It will go, or should I change the color to something else? Let's choose a different color. Let's say this purple. So starting from here, you will see that the S has a parent O, and then S has a parent. I think here we made a mistake. So this is not, S has a parent and not O. Yes, that was a mistake. Here was a mistake. Because we came from N, and so it has a distance of 9 and the parent N. Now we can start. So from node S, or the target node, we follow just the parent node. From here we go to node N, and node N has a parent O, and node O has a parent P, and node P has a parent K, and node K has a parent I, and node I has a parent D, node D has a parent of C, node C has a parent B, and node B has a parent A. So this is our shortest path, and its distance is 9. Total distance is 9 steps. And yeah, so we have successfully discovered where the goal is located, and also we have find the shortest path to the goal. The other distances, if you follow, see, they are longer. If you follow this distance here, the other cell, it will be a longer distance, at least one step longer. It will be 10. And you can also achieve this 9 with alternative distances also. For example, if you follow here 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are other possibilities also. You can get same distance, same length using other combination of cells also. But how we prioritize our how we arrange these cells alphabetically. So the breadth first search algorithm, it has given us the path according to this arrangement. So yeah, so this is the end of the breadth first search algorithm, and this is very useful algorithm. You have seen it's very simple also, easy to understand. But its negative point is that it works only with unweighted graphs. But if we have weighted graphs, then we shall see what we have other algorithms for these types of graphs.